Okay, so the homework we'll go over and then do the notes and introduce a little bit of new material. That's good. Okay, so you had 10-1 on donations for United George Fast Track. You had a United Way. They gave you the data, excuse me, for 10 people and each of their pledges. What is the best estimate of the mean? All you had to do is calculate the mean. It's suggested to do it in Excel. And you should have gotten a mean, was it 30? I believe $30. Yes. And the standard deviation S was 31.09? Yes. Okay. Anybody have trouble with Excel? Okay. So that would be the best estimate of the standard deviation. And then they wanted you to do a 95% confidence interval between two values that George can be 95% certain the mean value lies. Remember that was the x bar plus or minus the standard error times a t. So we have our x bar of 30 plus or minus. The standard error is given by the equation by the standard deviation divided by square root of n. And the n, or sample size they gave you, was 10. So the standard error would be 31.09 over the square root of 10, which was, I think, 31.316. Okay, so you're going to have 31.09 divided by 3.16. Yes. Correct, okay. To get 9.84.
Yes.
Yeah. As your standard error. 9.84. And the correct t, you've got an n of 10, so degrees of freedom n minus 1 is 9. In your t table for 95% confidence was 2.27.
Check.
So there's your range when you calculate it out. So it's going to be 30 plus or minus 22.34. So the range, the low would be
7.66.
766 to $52.34. And that's the 95% confidence range or interval that he can be certain that the average donation is between. Fairly large range. Questions on 10-1? Okay, so you also had 10-3, which was the sanitation workers and trash pickup. Okay, so last year the crews could collect 124 tons of trash per day. They want to test out these new machines, so they took a sample of 100 truck days. So your N's 100. The sample of these new trucks had a mean, which is x bar of 130, with a standard deviation S of 30 tons. Basically, you need to answer whether these new trucks are better than the old trucks. So some of the information to get at that, to do your equation, you do your standard error, S over the square root of n. So you're going to have 30 over the square root of 100, which should come down to an even 3 for your standard error. So these new trucks pick up an average of between 130 plus or minus your standard error, which is 3 times a t. for infinity degrees of freedom, it should be 1.96. So you're going to get 130 plus or minus 5.88. And so we're 95% confident that the trucks pick up the new trucks between 124.12 to 135.88 tons. And so this is our 95% confident new trucks pick up between 124.12 and 135.88 tons. They were comparing it to the old trucks of 124, and 124.12 is greater than 124, so yes, 95% confident new trucks are better. I could also say. If you did the T equals X bar minus mu over the standard error, if you did the comparison figure method, your T would have been 130 minus 124 over the standard error of 3, which you would get an even T of 2. And if you looked in your T table for 99 degrees of freedom, that value lies between 1.96 and 2.326, which is the 95 and 98% significant columns. So there's less than 5% error, or less than a 5% chance of getting 130 in the sample if these new trucks are no better than 124. So same conclusion, the new trucks are better.
Either way works.
Either way, yeah. Either way will work. Questions on 10.3. Okay. 10.6 wanted you to make your conclusion about adding corn oil to cattle feed and whether or not that increases their weight gain. So, they believe that adding corn oil will increase the cattle's weight gain. Last year, the cattle gained an average of 12.7 pounds. A sample of 30 cattle, n equals 30, had the following results. A sample mean of 14.1 pound increase, standard deviation of 5. What can you tell the department? Basically, we're getting into hypothesis testing now, and we'll discuss another way of looking at these the first part of the lecture. But you got a null hypothesis and a research hypothesis, usually labeled HO and H1. So the null is of no effect. Did you cover those in research design, null hypothesis? Okay. So this would be adding corn oil has no effect. And then your research hypothesis stated positively would be something like adding corn oil increases weight. Getting to the point of actually testing this with the sample data. So when you do your range, we're going to be 95% sure that adding corn oil to the feed will increase weight by X bar, 14.1, plus or minus your standard error is going to be 5 over the square root of 30. .91. I'll move that over here. And for an n of 30, you have degrees of freedom of 29. So for 95% confidence column, for 29 degrees of freedom, the T you would use would be 2.05. And your 95% confidence range is going to be 14.1 plus or minus 1.87. And you're going to be 95% confident that the cattle gains between 12.23 and 15.97 pounds. So this is the 95% confidence interval. 95% confident weight gain from corn oil is between 12.23 and 15.97 pounds. We were comparing this to last year's weight gain, which was 12.7 pounds. So last year they didn't add corn oil. The average weight gain was 12.7 pounds. This year they did add corn oil. It looked like from the sample that it did increase the weight, but when you calculate the confidence interval, we can only be 95% sure that the weight gain was between 12.23 and 15.97. Sure, it could have been 13, 14, 12.8 pounds, but it could also have been less than that 12.7 from last year. The weight gain could have actually gone down from last year. 12.5, 12.3, all the way down to 12.23. So you would say you cannot be 95% confident adding corn oil increases weight. If you'd done a T, the x bar minus the comparison figure mu of the standard error, you would have gotten 14.1 minus 12.7 over 0.91 for a T of 1.54. And if you go to your T table, you've got 29 degrees of freedom. So you're in that row. You're looking for 1.54. It lies between the 1.311 and 1.699, or between the 80 and 90% confidence, which means that there's between 10 and 20% error, which is bad. We want 5 or less. And so you would come up with the same conclusion. We cannot be 95% confident. We're only 80 to 90% confident, which is not good enough in social sciences, so same conclusion. Didn't work. Questions on 10.6. And I believe we did 10.17 in class, right?
Yes.
Does anybody have questions or need to see 10.17? I did the same for the other class too, so. Any problems with SPSS? The SPSS this week was much more involved in a bigger component. Any problems with the data, with the videos, with anything? No, yeah.
That was good.
Okay.
Videos made it simple.
Did it take forever to upload because the sample
The first
size?
one did.
The first one with the 100. Was it less than 5 minutes?
Yeah.
Okay.
A couple minutes.
Okay, so number 5, fire response data set. You had to do turnout time variable, find the mean, median, and standard deviation, which I got a mean of 73.84. Does that match? And a standard deviation of 35.120 and a median of 69 seconds. So what you see is that you see that the mean is greater than the median. It means outliers are it's skewed positively. It means outliers at the high end are pulling the mean toward it. So yes, it has skew. You know that because the mean is greater than the median. So it's a positive skew. Questions about 5?
Could you have also put that because the standard deviation is above plus or minus 3, it shows that it's skewed?
No, because it's the relationship between the mean and the median.
Good.
Others? In 6, you need to do a histogram, which should have been the second video. And it almost looks like a normal distribution, but if you look, it's not quite. And you could have figured that out from these descriptive statistics, but if you go out to the large numbers or seconds, the tail, that's bringing the mean towards it. It's not perfectly symmetrical. That tail on the right end is extending outward. So questions on 6? Okay. 7 had you split the turnout time variables based upon whether or not the units responding to the emergency had been trained in improving their turnout times versus not being trained. So your mean for so you should get when untrained, so that means that the training completed variable was 0. A unit responding had not undergone the training yet. They had a mean turnout time, I think it's 74.18 seconds. When they were trained, or the training completed, variable equaled 1, the mean turnout time was, I got, I think the wrong one.
64.27.
Yeah. 64.27, yeah. So the question was, does it appear the training worked? On the surface, yeah, but we don't know statistically. You didn't need to calculate whether or not the training worked. In fact, for the next homework assignment, you'll do a t-test in SPSS to determine if these trained groups are statistically different than the untrained groups. It's about 10 seconds. You'll be able to determine whether or not you can be 95% confident that the training worked or not.
I copied the wrong chart or something. Wow, okay.
Did you do response time?
That's what I did.
Okay.
I did response time.
Yeah, so
Yeah,
in the homework you had to do the turnout. So it's not going to be anything major.
Okay. Shoot.
The other data for turnout time was I wanted you to split up the average turnout times between whether or not the units have a chief, fire chief, or a supervisor at their station. So without a chief there, so that's the chief variable equals 0. The mean turnout time, I got 69.55 seconds. When the chief is at the station, so that variable from the code book equals a 1, I got 68.52 seconds is the average turnout time. Does it appear, there's really no right or wrong answer. If you say yes, because 68.52 is less than 69.55, yeah, it appears that it does. But if you also said not really, because it's only a second, that's fine too. This week, when you run SPSS, you're going to determine if this difference is statistically significant, and we can be 95% confident that the presence of a fire chief pushes the personnel to turn out faster, to hurry up and get in their emergency apparatus. But for right now, it's just appearances, it's just looks. We haven't tested statistically yet. All right, questions on the homework? Okay. Since we're still doing this, let's go to the notes on the more on t-tests. Basically, what we're trying to do here is test hypotheses with t-tests. And when you calculate your t-score and you calculate the confidence interval range to determine if a program worked, you're testing hypotheses. In the same case here, you could test the hypothesis that the presence of a fire chief decreases turnout times, and then you can statistically test it, which you'll do for the homework. There's another way of looking at these t-tests that we've done. You'll come up with the exact same conclusion, but you begin with this manner to think more in terms of hypothesis testing. So what we'll do is, there's a conceptual example on the first page from just numbers that I made up, and then we'll apply it to the problems that you did for the homework. Basically what we're going to end up doing is drawing a t-distribution, which is going to be just your normal distribution. And we're going to put a comparison figure at the peak. And then you're going to test if your sample mean is statistically different from the mu, the comparison figure. No different concept from last week. If you do a 95% confidence range using the X bar, it's standard error, you can determine if it's different than mu. If you calculate a t-score, you can do the same thing just from the homework. What we'll do today is just a third way of looking at it and answering it. What you will do is you will calculate the t-score for that sample mean just like you did if you did the second process of the homework this week. We're going to take a look at the X bar minus mu over the standard error. Again, ways 1, 2, and 3, you're going to come up with the same conclusion. This is just another way of thinking about the problems. Okay. All three ways can test hypotheses. It just depends upon which version you like better in terms of interpreting the numbers. And I've given some example numbers in the steps here. but I think it'd be better to just follow these steps with an example, and there's room for examples on page 2. So all the figures and numbers on page 1, like suppose your sample mean is 10 with an n of 16. Right? That's what the steps in the notes pertain to. I think it's going to be better if we do the steps with an example that you've seen from the homework. So, let's see. From the homework, let me find an example of one where the program worked and where the program didn't work. So, we're going to do 10.3 and 10.6 again. But test it using the steps mentioned on pages 1 and 2. The third way of viewing these. So 10.3 was the old garbage trucks versus new garbage trucks. So last year, our comparison figure was 124 tons. This year, they took a sample of, was it 100 truck bays? And these new trucks. So they're going to compare the new versus the old. The sample mean was 130 tons with a standard deviation of 30. Ultimately, we're trying to figure out, are these new trucks better? We only were able to take a sample of 100 of the new trucks out of the full population of new trucks that exist. It's not possible to test all the brand new trucks of 1,000, so we took a sample of 100. The new trucks are 130 tons. They appear better than the old trucks from last year. I'll mark new, old. When we calculated the interval, remember the standard error was 30 over the square root of 100, which was 3. And our degrees of freedom, n minus 1, was 99. So nothing different from the homework. In fact, if I'm going to do all 3 ways, the homework, you had x bar plus or minus the standard error times the t. And that was 130 plus or minus 3 times the t value for infinity degrees of freedom of 1.96. And so the range that we got for the population of these new trucks that were 95% confident was between, what, 124.12 and 135.8, right? And based upon that, we said these new trucks are better. Remember, we said that 95% confident new trucks better. New trucks better. What you did was implicitly test the hypothesis that new trucks pick up more tons than the old. That's your research hypothesis. Was we're going to hypothesize that these new trucks are better, more efficient, they pick up more tons per day. We took a sample of 100 of the new trucks, the average is 130. It appears bigger than 1/24 from the old trucks, but we need to statistically test that. And we know that the true population, the true mean of these new trucks, how much they pick up is between 124.12 and 135.88. And so we said we were 95% confident the new trucks worked or were better. We'll support a hypothesis, right? We found support. If you calculated the t-score, you did 130 minus 124 over 3 to get a t-score of 2. And you remember in the T table, that meant we were 95% and 98% confident that the new trucks were better. It was way number 2. And based upon that, do we find support for the hypothesis? Yes. We can reject the null hypothesis. That's usually what you want to do, is reject the null, because the null hypothesis has no effect, no difference. Typically want to find support for your hypothesis. So in this case, both ways said there's support for the hypothesis. The null hypothesis would be no difference in the trucks in terms of what they pick up. We can reject the null, which is a good thing. Reject the null or accept your hypothesis. So we came up with both of those conclusions. Another way to think about this is the third way, by drawing a t-distribution. So just draw a normal distribution, perfectly symmetrical. At the peak, put your comparison figure, or your mu, which we were comparing from last year, so that was 124. Okay. So these are following the steps on page 1 now. Draw your t-distribution. Put the comparison figure at the peak. Okay. Calculate your degree had at 99, right? Basically, we're going to normalize now this 124 to 0, like we did with the z-scores. So the 124 corresponds to a 0. Go to your t-table on page 452. For your 95% significance and your degrees of freedom, what is the magic number of 95% statistical significance at 99 degrees of freedom? 1.96. So this can be considered a t-critical value, plus or minus 1.96. That means to obtain statistical significance, to have a statistically significant difference between the new and the old, you need to get a t-score that meets or exceeds 1.96 in either direction. So in your t-graph, put in, because we normalized the comparison figure to a 0, put in to the right positive 1.96, and to the left, because we want to do a two-tailed test, a negative 1.96. And to the right and left of 124, respectively, because we normalized 124 to a score of 0. And draw up in the curve, and then shade everything from 1.96 out to the right, shade everything from a negative 1.96 out to the left. Essentially, these shaded regions mean exceptional cases, and you can think about it as being more than 1.96 standard deviation units away. If your t-score that you calculated, like on your homework, if you did the second method, if your t-score meets or exceeds the t-critical value, then you have statistical significance. And so you just use this same equation. Now you can just call it t obtained. Okay? And this is obtained from your sample. So we've set a threshold, which is a t-critical, for 95% confidence, 95% statistical significance. Your T obtained needs to meet or exceed that. And our T obtained was 2. So put 2, mark off where 2 is. Well, it's just a hair to the right of 1.96. But it's in the shaded region. It's in the critical region. Anytime you're in that critical region, in terms of hypothesis testing, doing a t-test, you have statistical significance at the 95% confidence level. So the conclusion is still the same. 95% confident new trucks are better. You can say we found support for the hypothesis with 95% confidence. The conclusions are exactly the same. I've just introduced the idea of testing a hypothesis. And you could have answered this, or you can answer it for the homework for next week, either of 3 ways. It's just whichever way you tend to think a little bit better in terms of hypothesis testing. If you like that range and can apply that range method, the X bar plus or minus standard error times T, to determine if a program worked or if new trucks are better, great. If you're thinking in probabilistic terms and like to look at the percent error, in the second method where you just calculate the t-score and you see where it falls in your table, great. I'm more of a visual person, and this is the way it was taught to me in statistics. And so I like to see the critical region and see if my t obtained, 2, falls within the critical region. Same conclusions, essentially testing the same thing, just in a different manner. Questions before we do another example? Okay, let's look at the cattle one. So I have a null hypothesis and a hypothesis. So on 10.6, remember you had the cattle, and determining whether or not adding corn oil to their feed increases their weight gain. Your research hypothesis, which should state a direction, logically would be adding corn oil increases weight. And the null hypothesis is of no effect, which means adding corn oil has no effect. We know from the homework that it did not have an effect. We could not be 95% confident that adding corn oil increased the weight gain. In fact, the 95% confidence range was 12.23 pounds to 15.88, 15.97. So just keep that in the back of your mind that you were 95% confident that the weight gain was between 12.23 and 15.97. So last year, without corn oil in the feed, weight gain was 12.7 pounds. This year, we took a sample of 30 cows that had undergone corn oil fortified food. We want to see if their weight gained. Their weight gain was, of the sample, 14.1 pounds with a standard deviation of 5. So in this case, it it looks like there's a weight gain. In fact, 14.1 is greater than 12.7, but is it statistically different? Can we be statistically significantly confident or confident with 95% assurance that, yes, the weight gain was 14.1 pounds, or that adding the corn oil works? The standard error we said was, let's see, 5 over the square root of 30. It was like 5 over,
I don't know, with 5.48,
it was like 0.9 something.
0.91 was
Point
standard
nine.
error.
Okay. 0.91, and our degrees of freedom was 29. So with the new method, and the third way of looking at these types of problems, you draw a t-distribution, which looks like a symmetrical normal distribution. You put your comparison figure at the peak, which was 12.7 pounds last year. And that gets normalized down to a 0 t-score slash z-score, because t and z become the same after n gets above 32. You now need to find your threshold for statistical significance, or your t-critical value, for your degrees of freedom and 95% confidence. And 29 degrees of freedom, 95% significance. Your threshold that you need to meet or exceed is 2.05 in either direction for a two-tailed test. So just to the right here, do 2.05 and shade. And if it meets or exceeds that, it would be a statistically significant weight gain. If it's negative 2.05, if your t-score ends up being negative, then it's a 95% statistical significant decrease in weight gain, but we know that that's not likely going to be happening. So those are your threshold markers at plus and minus 2.05. Your t obtained is just the t equation, x bar minus the comparison figure over the standard error. And that is 14.1 minus 12.7 over the standard error of 0.91. 1.54. Where does 1.54 now fall in your t-distribution graph? Somewhere between 0 and 2.05, so 1.54 in the white region. If your obtained does not land in the shaded region, if it lands in the white region, not statistically significant. So remember, our conclusion was something to the extent of cannot be 95% confident. Adding corn oil increases weight. We said we can't be 95% confident that that program of adding corn oil worked. So we cannot accept our hypothesis with 95% confidence. Which, in research design, you may have heard, cannot reject the null hypothesis. So ultimately, your research hypothesis that adding corn oil increases weight is not found to have any support at the 95% level. You cannot say in either case there's never any proof, because there's still some amount of error. There's still, maybe a 5% or less chance that adding corn oil works, but we can never be certain. You're never going to be able to prove something with sample data. If you had the true population, you could do a proof, but when you're dealing with samples, even when you're at 99.9% confidence, there's still a 0.1% chance of error. So usually you can't say my hypothesis is proven. You just say that my hypothesis is supported with 95% confidence or at the 95% confidence level. Yes?
So a researcher or a scientist would never say 100%, right? They would always say 99.9%. There's always that error that...
In a social science setting dealing with human behavior where there's a lot of randomness, yes. Now, if you're dealing with like gravity in a vacuum and doing mathematical equations, then those are laws. Then that's 100% because those are scientific laws. With social sciences, never can you really be 100%. You'd be pretty close. Notice what would happen if we change the confidence level. Say, for whatever reason, we don't want to be 95% confident, but we want it to be 80% confident. 80% statistical significance. You're not going to do, but it's good to see a conceptual exercise of this. What happens is, what does your new critical value become?
1.31.
Yeah, 1.311. Does everybody see that?
Right.
For 29 degrees of freedom, 95% statistical significance. Our T critical goes from plus or minus 2.05 to plus or minus 1.311. So it extends the critical region in both directions, essentially. Makes it easier to find acceptance of your hypothesis. With an 80% threshold, we would have found that 1.54 fit in the shaded region, but 80% confidence is not good enough. Basically, the less confident you want to be, it becomes easier to accept your hypotheses, but you're not really that confident. 80% probability of your hypothesis being correct, pretty low. If you wanted to go beyond 95, notice that the critical region shrinks and it becomes harder to accept your research hypothesis. All right. Other questions? We'll do one more example because in your homework you will have a similar problem. We will do in class 11.1. Looks a lot like 11.2 on your homework. So page 198 in the 9th edition. Is this more confusing this way, or is it clearer? Or...
It's clear. It's clear.
Clear. Does anybody prefer? Who prefers the range method? One. Who prefers the second method where you look at the amount of error? One. And then who prefers the picture? No. All right, we'll do the next one. All three ways, and you come out with the same conclusion. Okay, so 11.1 talks about cost of repairs for city's automobile pool. It says last year, Normal, Illinois had all car maintenance on the city's automobiles done by the city pool. The cost was $364 per car, so that's going to be our comparison figure, $364. This year, the city officials fired all the workers in the maintenance pool and are using Jack's Crash Shop to perform the maintenance. They would like to know, without doing a complete audit, whether Jack is saving them money. A random sample of 36 cars, so there's your N of 36, showed a mean repair cost of $330. So it looks like it's less than $364, with a standard deviation of $120. What can you tell the city officials? Basically, you're testing a hypothesis that the private pool, private maintenance is better than the public maintenance. So that your hypothesis would be Jack's auto is cheaper. Null hypothesis, no difference between Jack's and the city mechanics, or something to that extent. Null hypothesis of no effect. The hypothesis is that Jack's, we'll say, is lower. It appears lower just by numbers, but statistically we need to test that. So if you do the first method, method number 1, you can do x bar plus or minus the standard error times the t to get your 95% confidence of what the true population mean of Jack's auto repairs cost, because we were only able to sample 36 of Jack's auto repairs. So you're going to get 330 plus or minus. Your standard error is s over the square root of n, which is going to be 120 over the square root of 36, which is 120 over 6, which is 120, I'm getting tired. 120 over 6, yeah.
Which is 20.
Yeah, I'm off. 120 over 6, which is 20. Right? It's been a long day. So your standard error is 20. So with your 95% confidence, it's going to be 330 plus or minus 20 times the t for, let's see,
The 20.
35 degrees of freedom. Yeah, it's going to be the
1.96.
infinity row, which ends up being 1.96. Let me know if I'm going too fast or need more explanation. So 330 plus or minus 20, 1.96 is for 35 degrees of freedom, so you're in the infinity row, and when that hits the 95% sig column, it's 1.96. So our 95% confidence of how much Jack's auto repairs the average truly costs is 330 plus or minus 20 times 1.96.
39.2.
39.2, so your range is from,
290.8.
yep, $290.8
369.
to $369.2. Okay, so last year's maintenance with the city, workers cost $364. They switched to Jack. Sample was $330. We're 95% confident that the true average maintenance cost for Jacks is between $290.8 and $369.2. So when comparing to last year, think about cost, is Jack's cheaper?
No.
No.
It's not in the range.
And we're thinking about
Outside
it.
of the range.
Yeah, it's out of the range, and we're thinking instead of being on the right side of the curve now, we're looking at the low number. We're now looking. We're dealing with cost. We're dealing with the other end of the range. It is possible that Drax truly does cost $290.80, which is way less than $364. But it is also possible for Jax to cost an average of $369.20, which is $5.20 more. So you cannot be 95% confident Jax is cheaper.
Because we started at what, 364?
Yeah. So last year it was costing $364. Yeah.
Could we not just take the standard deviation of 120 plus the 130, and that's 450, and automatically know it's not going to be within that range?
The 330.
So we know that's over 364 from the jump start. So could we say right then that it's not going to fall into 95% confidence?
You would have to do. I don't think so. It would depend upon how your n changes because it's in a standard error. So let me think about this. So 120. Trying to see if you could get the n to be really, really tiny. Look. If your n was up to 100, then you'd have 120 over 10, which would be 12, right? And then you would change this multiplication to 12 by 1.96. 12 times 1.96 plus or minus 23.52. So no, because if you increased your sample size to 100, it still had the same standard deviation. Your standard error would go down to 12, and your range would be 306.48 to 22, is that what I said? 23. 330 minus 23.52. To 353.52. And in that case, it would be cheaper. Yeah, so no, you can't just look at the standard deviation. If your n goes up and you have the same standard deviation, your n goes up, your standard error goes down, it's going to shrink that range, and it could shrink the range to where the 95% confidence is $306 to $353, which is cheaper than $364.
I guess what's throwing me off is standard deviation means that there's at least one payment out there that's $120 more than the 330. Is that correct?
Yeah, that'd be a fair assessment of that. Yeah.
So then, to me, that means there's at least one payment out there that's $450, which means it's more than 364.
But what if that was only one out of 36?
That's not
What
true.
if that was the only outlier?
I see.
Yeah.
I got you. Okay. Thank you, guys.
Yep. Okay. So, all right. So we said we were not 95% confident. Put the original numbers back up there. And 36 over 6, 20. 20. If you wanted to calculate with the probability of error using the second method, and t equals x bar minus mu over the standard error, your t would be 330 minus 364 over 20. Negative 34 over 20, negative 1.70.
Is there usually different market, Dr. Shell?
Oh, yeah. Yeah, I'll use the black. Let me redo it. T equals x bar minus mu over standard error. 330 minus 364 over 20. Negative 1.70 is your t. And so when you go to your t table and look at, let's see, 35 degrees of freedom, you're dealing with the infinity row. You're looking for where 1.7 is. It's somewhere between 90, we're 90 to 95% confident, somewhere in between, which means that we have between 5 and 10% error, which is not good. We want it 5 or less. We know it's somewhere between 5 and 10. So with that, you cannot be 95% confident that JAX is cheaper. Don't have support for your hypothesis. If you did the third manner with your t distribution, and you put the comparison figure at the middle, which was 364, standardized down to a 0. Your t critical value is 1.96, what we used in the range equation. So 1.96 off to the right, negative 1.96 off to the left. So our t critical is plus or minus 1.96 for that 95% statistical significance. Our t obtained that we calculated just now is negative 1.70, which is in the white region. 1.7. It does not meet or exceed negative 1.96, so same conclusion. Cannot be 95% confident that JAX is cheaper. Cannot reject the null. Not, yeah.
Do we have to do it this way?
No, which of the 3 ways you like better?
Okay.
As long as you come up with the same conclusion. Questions about?
I'm snagging myself on something stupid probably, but in this example, are we disproving both the null hypothesis and the hypothesis itself? Because the hypothesis, the null being there is no difference.
So you would say we accept the null hypothesis. Yes. So you want to reject the null, because if you reject the null, you accept your research hypothesis.
Right.
But if you accept the null, we're saying we're accepting that there's no difference.
Right. But
That means we reject our.
in this case, aren't we rejecting both? Because they're not the same. And JAX is not cheaper.
Let's see.
Or am I
So
overthinking?
I think so. So when you say we, in this case, do you agree that we accept the null hypothesis?
I mean, if you say so, I will. But
Does that make sense?
Like, to my mind, we don't accept that. Like, we reject the null because the prices aren't the same. Aren't they different?
Statistically, no. What do you mean between 330 and 364?
Yeah, I was thinking if the null is accepted, that means the old mean and the new mean would have to be exactly the same.
Statistically,
Right.
that's what it means. It means that there is no difference between 330 and 364.
So you could pretty much off the bat say that you don't accept the null. And if you see those two numbers being different, you can pretty much say that I'm not accepting the null.
See, that's I'm
Okay.
stuck where Troy's
Okay.
stuck.
Okay, gotcha.
'Cause
So-
they're not literally the same. I understand what
Talking
they're
about a
saying.
range that's acceptable.
Meet the same range.
Right.
Not being
So what was
in the mean.
the range we had calculated was? Let's see if I remember.
290.8.
369.
369.2.
Okay. So we're 95% confident that the true population of jacks is between that number.
Correct.
Right.
We only have a sample of jacks, a sample of 36 with an average of 330. Okay, we're trying to extrapolate up to the true population of jacks.
Right.
And essentially what we're saying is that, okay, so your X bar, your sample average was 330, our comparison was 364. Remember again, this sample is only out of 36, it's not of the true population. We said that we accept the null, right, is what we're saying, and that we cannot support the hypothesis. Right?
Mhm.
Okay. Statistically, the sample mean, okay. Statistically, the sample mean from Jack's population is not significant. That 330 is not statistically significant, right? It means that that the population of Jacks, whatever thousands of auto repairs he does, is not 330. It also means, and we didn't really cover it, it means that the population mean of Jacks repair costs are statistically no different than 364. Meaning that, let me think of a better way to explain it.
So it's
not-
just the
So
semantics of the null.
It's, yeah, it's
There's
just,
no statistical
Yeah.
difference between.
Because you can't reject it.
you can't, right,
Only reject it by 95% confidence.
Because-
that it's
We
not
can't-
different.
right, we
Because it's
can't,
in the statistics.
we can't say that the true population mean of Jacks is different than 364,
Mhm.
more or less. We had a sample of 330, which looked less. That 330 was not statistically significant. What that means is that when you extrapolate up to the population of all of Jack's repair, it's no different statistically than last year's city pool was 364. So no, statistically, there's no difference between last year's 364 and Jack's.
I understand. And as the sample size grows larger, that
Right.
margin, which I understand.
Yeah, basically we cannot conclude that Jack's is less than 364 or greater than 364.
So if we
Right.
cannot prove the hypothesis, then we have to accept it.
Yes,
Yeah,
I was asking.
exactly.
You have to have one or the other?
If you have no, you cannot have both.
Null meaning it's
You
a
can
neutral
you reject
statement.
both?
Right.
Cannot reject both.
Okay.
You,
Got it.
Because
Okay.
null
Got it.
is, it's neutral, it's an innocuous statement.
Right,
It doesn't
so-
mean anything.
so if you find support for your hypothesis, you reject the null.
Okay.
If you find no support for the hypothesis, which we just did,
accept it.
you
You
accept the null.
Okay.
So their ops can't have both accept, can't have both reject. When one's accept, the other's reject, and vice versa.
I think I was thinking like, I'm
So to
sorry.
answer
Yeah,
this,
too
so
literal.
you could
Yeah.
say, we accept the null that Jax is not cheaper than,
Not
last year.
statistically different.
or is
Right.
not statistically, or we can just say, we cannot reject the null, which is basically saying the same thing.
Exactly.
It's the same.
Just
Both
a
are
different-
fine. Yeah.
So if there was 360, if that number, so 369, if it was 363, then we would accept the,
Hypothesis.
exactly, right?
And reject the null. Yeah. You would, if this was the range, you would say we reject the null because 363
It's cheaper than
is
364.
364. So we reject the null of no difference. So we accept the research hypothesis that Jax is cheaper with 95% confidence.
It's just because Jeff overcharged that one time.
Could be.
And the engine replaced.
All right, questions so far? Quickly before we break and go on to chi-square, you'll see in the notes. Where did I put the notes? Where's Adam? Okay, we've covered section 2. Section 3, we're not really going to cover the difference between one and two-tailed tests. We're just going to use two-tailed test. I don't know what Dr. McDonald says for your class. If he says do a one-tailed test, let me know. For the capstone, we'll cover it. Tend to use two-tailed tests because they're the most conservative, and two-tailed tests are harder to reject the null. And if it's harder to reject the null, and you actually do reject the null, you're more confident in your research hypothesis. In the homework that you'll do for SPSS, it will tap into independent versus dependent samples. For this class, you'll be doing independent samples t-tests. You don't see many instances of dependent samples tests. A dependent sample is you look at the same exact group of people over time. You track them. So if you followed a sample of children from kindergarten through high school on, I don't know, vital health statistics over time, you're dealing with the dependent samples because it's the same people over time. More often than not, you're going to be dealing with independent samples where it's not going to be the same people all the time. And so in SPSS, you're going to do independent samples t-test. What you'll see for the homework is, remember we had turnout times for whether or not the unit had been trained. So the trained units turnout time, or the time it takes them from the time they hear about the emergency to leaving the station, was 64.27 seconds. Untrained units took 74.18 seconds. So essentially what we did was test whether or not the training worked and help them get out of the fire station faster. Null hypothesis, H0 would be no difference between trained and untrained. And a research hypothesis would be that trained have lower turnout times. This is getting into kind of like an experiment. Here's your control group with an N, a sample size, which there's a sample size in that data set, an N of a number, and a sample mean is, let's see, the control group of not trained, X bar was 74.18. Standard deviation was train completed 0, standard deviation 31.69 versus an experiment group that had been trained. There was an N, number of trained. The mean was 64.28 seconds with a standard deviation of, let's see, training 1, standard deviation was 31.51. You can now test the difference between these groups that have different N's, different standard deviations using a software. in SPSS. It's slightly different than the t-test that you've been doing because even if the untrained was the comparison figure at 74.18, we now know the standard deviation of the untrained. Remember in all the homework problems, we were just comparing it to a number of average. Well, now we're adding more information. We actually have a standard deviation for the untrained, and we have the standard deviation for the trained. So we essentially are testing the difference of means between two samples, a sample of untrained, a sample of trained. If given all this information, you could, in chapter 13, do the really long test by hand. And they've got a gigantically long equation to do a t-test for two samples, two different standard deviations. But SPSS will do that for you. So you will be able to determine whether or not these means, difference of means, is statistically significant. Is the trained mean lower than the untrained mean with 95% confidence? Did the training module work? Did it improve their performance or not with 95% confidence? And so that's what you'll be using these t-tests for in SPSS. The other one was whether the chief was there. Chief present, chief absent. We saw that when the chief was absent, the turnout time was 69.55 seconds. Absent, 69.55. And when the chief was present, it was 68.52 seconds, the average. That's an X bar, that's an X bar. Okay. The presence of the chief decreased turnout times. Well, with the data set that exists, you've got two samples, two means, two separate standard deviations. Now you can do a difference of means test. So essentially it's kind of like an experiment. Chief absent could be your control group, and then hey, we put in the chief at the station. That's kind of like an experiment group. But the supervisor there is performance improve. Questions on that before we break? And there are videos on how to do that in SPSS. In fact, 4, I tell you conduct an independent samples t-test to determine if there's a difference in turnout times for trained versus untrained. What can you conclude? And then for the fire stage, the chief at the station or not, what can you conclude?
Turnout time.
Turnout time, yeah. That's the time from when they get the dispatch from 911 operators to when they leave the station.
Is it important to which one you assign as the control and which one you assign?
No. In this case, no. In this case, yes, because we said we did an actual experiment where we said certain groups are not going to get trained and then certain groups are going to get trained. So that'd be more of a typical. Here in this case, it doesn't really matter. You could say the experiment was removing a chief or then putting in a chief. All right, let's take a break. We'll quickly go over chi-square. In fact, the example in the notes is the homework problem in the book. So you'll have one of the answers, and then I'll show you what to do with SPSS.